a particle at rest in the expanding universe. And fixed comoving distances correspond to exponentially growing physical distances. We have translation symmetry in these comoving distances. We have a corresponding conserved momentum and wave functions that go e to the ikx. I normally quote results in Fourier space. And if you have a fixed momentum k, that corresponds to a given comoving distance and corresponds to a physical momentum, which is very small in the future. Physical proper momentum is very small in the future. That corresponds to very long distances, proper distances in the future, but very high momenta in the past. Okay. There is a horizon, so if you have two particles separated by a fixed comoving distance, at some time this particle loses causal contact with the other particle. And that happens when eta is equal to x. So if we are looking at some separation, let's say some delta x, and we go to times which are smaller than delta x, then we'll be outside the horizon for those distances. Okay. In momentum space, that occurs when k times eta is of order 1. So if we follow a fixed k mode, so a fixed comoving distance, at early times that corresponds to a physical momentum. And so for large physical momentum, that wave doesn't feel that the wave is in de Sitter space. It feels as if it was in flat space. And so we can choose for it the usual vacuum, the usual flat space vacuum. And that corresponds to the choice of vacuum, which is called Banach-Davis or Chernikov-Tagerov or Hartle-Hawking. And looking at the fixed k mode at late times corresponds to looking at super horizon distances, as I mentioned before. So if we have a theory of pure gravity, we are interested in looking at, for example, metric fluctuations. So we can write the metric in this way. We scale out this factor of eta squared, and we look at these metric fluctuations. And these gravity wave fluctuations, defined this way, become constant at late times. The wave function, if we computed the wave function as a function of the metric, it becomes independent of this overall scale factor and becomes a function which depends only on the conformal structure of the metric. So the Wheeler-DeWitt wave function is, it's time independent because of the reparametrization symmetry, and the physical time dependence is encoded in the scale dependence of the wave function. This is true up to an overall phase that I'll discuss later. So for a physical mode in the leading approximation, the wave function is a Gaussian, so one can compute it using free fields in ADS in DS by expanding the Einstein action, and one gets this well-known answer, which is a Gaussian. So this is the usual statement that inflation generates Gaussian perturbations, in this case Gaussian spectrum of gravity waves. H is the metric fluctuation. This k cubed just comes from dimensional analysis and is proportional to the Planck mass squared, so to 1 over g Newton. So for large, normally when we can trust this approximation, m squared is much bigger than h squared, and so we'll have very small fluctuations. We could consider computing corrections to the Gaussian approximation, and the simplest correction would be to compute the 3-point function. And that can be computed directly by expanding the Einstein action to third order. And in this particular case, we can do something without actually doing the computation, because conformal symmetry actually restricts its form in the same way that it was restricting this form. This factor of k cubed just comes simply from scaling symmetry. For the case of the 3-point function, we similarly they're constrained by conformal invariance up to 3 different possible shapes. So there are 3 constants that are not fixed by conformal symmetry. One of the constants is fixed by essentially word identities or the reparametrization symmetry, and that's the shape that comes from the Einstein gravity action, produces one of these shapes, and the other 2 shapes come from higher derivative corrections to the Einstein, can be realized in terms of higher derivative corrections of the Einstein theory, in terms of the Weyl tensor cube. And there is also a structure that essentially also the Weyl tensor cube, but contracted with an epsilon tensor, and that's a structure that violates parity. So This 3-point function, therefore, you can be computed as long as the gravity or string theory is weakly coupled and doesn't rely on derivative expansion in the bulk theory. So even if the Hubble scale is comparable to the string scale, we still have this 3-point function. This family, 3-parameter, well, it's essentially a 2-parameter family of 3-point functions. Now we could imagine computing all the 3 diagrams, and that would be, so all the diagrams in which we don't have any loops in the interior. So all these 3 diagrams give the leading contribution to the higher point function. So instead of considering the 3-point function, we consider 4-point function, 5-point function, etc. They are computed in terms of such 3 diagrams. And you can, as all 3 diagrams, they are computed by looking at classical solution of Einstein's of the equations of motion of the theory, in this case, Einstein's equations, and with special boundary conditions. So here, they are computed in terms of a solution of Einstein's equations with fixed future boundary conditions. So the metric has to have a specific shape here in the future. And in the past, we have this Bunch-Davies condition, which we discussed before. So we fix the metric in the boundary to an arbitrary shape. So here, this is the shape of the metric, let's say. Of course, it's a tensor, not just a scalar function, but we fix that shape. And we impose interacting Bunch-Davies boundary conditions in the past, which says that the solutions here in the past contain only positive frequencies. And that can be enforced by just simply saying that as you go to very negative conformal times and you rotate the contour slightly into the imaginary direction, then the solution should decay. This is, of course, the same as the usual Feynman boundary condition in flat space. And this prescription works to any order in perturbation theory. So we can compute all, even if we were computing loops, which will not be computed in this talk, but even if we were computing loops, this prescription works and allows us to choose the so-called interacting Bunch-Davies vacuum. And then you evaluate the wave function by writing e to the is, where s is the gravity action evaluated on a solution of the Einstein equations with these boundary conditions. And so you evaluate this action, and something important to note is that the solutions of these equations are not real, so this action is not a pure phase. This action will have terms that are a pure phase, and some terms that are the action, well, e to the I action will have terms that are pure imaginary, or also terms that are real. And the reason that that we have a complex action is simply because in the past we are putting some boundary conditions which are complex. We say we have positive frequencies but no negative frequencies. And this prescription is also the same as the prescription given by Hartley and Hawking to compute the wave function of the universe. One can derive it using perturbation theory, or and it also agrees with what you would compute if you took half of the Euclidean S4 and then you continued to the future in the Lorentzian evolution, and you took one of the oscillating expressions in the Hartle-Hawking wave function of the universe. You get this wave function. So that's, we're going to be talking about this. Now, the late time behavior, or equivalently, we look at the metric which has fixed features on comoving coordinates and then expand that metric very much. So that's the same as looking at the late time behavior. And we'll find that it has an oscillating piece, a phase, which goes like 1 over eta cubed. So eta is the time at which we cut off this expression. Or if you wish, eta over h is the metric at which we evaluate this wave function. And we put in this action, and we get a term which is proportional to the area of the future boundary, the regulated area. And so this is this oscillating piece I mentioned before. And it's similar to the divergent counter terms we have in the usual ADS calculations that you might be familiar with. And they would drop out from the computation of modulus of psi squared. And then there is here some other subleading term I'll mention in more detail later that is also oscillating, proportional to the curvature. And then there is a finite piece. Now, this finite piece is the interesting part, because this is the piece that will be real and will contribute to the modulus of the wave function. Now, notice that in principle, in the Wheeler-DeWitt equation, we should be computing something similar to the Klein-Gordon norm, except that, of course, we have to integrate over the many-finger timed, or we have to take a product of the derivative with respect to the scale factor at each point in space-time. But essentially what happens is that those terms cancel out. Well, the main dependence on the scale comes from this term, and then this gives a universal contribution. And so the modulus of the wave function is just simply the square of this quantity. This is the same as what happens if we were solving the Klein-Gordon equation. Now, this computation is very similar, very reminiscent of the computations that we do in Euclidean anti-de Sitter. And in fact, the Euclidean anti-de Sitter computation is also an evaluation of the wave function. In other words, when we compute the action of a Euclidean solution, imagine we have a Euclidean solution, an Euclidean anti-de Sitter solution, which ends on a specified metric on the boundary of ADS. We can calculate the wave function as a function of the boundary metric. That's the usual calculation we do for calculating the generating function of correlation functions of a stress tensor. So if we do that calculation is also essentially calculating the Hartle-Hawking wave function of the universe, but in this Euclidean region. Now, in fact, this calculation and this other calculation are actually related in a simple way. So there is an analytic continuation between Euclidean anti-de Sitter and de Sitter, which simply is this relationship that you take the radius to I times the radius, and this is the same that Nati was using in his talk. He mentioned the analytic continuation between anti-de Sitter and de Sitter. And that's the simple analytic continuation of the radius. And here, if we analytically continue C to IC, this is just simply an analytic continuation of the coordinates. We go from this metric to this metric. So that gives this minus sign. The minus sign here is cancelled with the minus sign that we get from analytically continuing the radius. So we go from this metric, the anti-de Sitter metric, to the Sitter metric. Of course, this is very trivial. Something that is less trivial is the fact that the boundary conditions also transform in an appropriate way. So if we added here a small metric perturbation, and here also small metric perturbation, then the boundary values, if they were real before, they will be real also in the other problem. And also the boundary conditions that we are putting in the interior of the space also transform into each other under this transformation. In other words, here, if we were doing a calculation in Euclidean anti-de Sitter, we would add a perturbation here to the metric, and we would demand that the metric goes to that boundary value at c equal to 0, but at c equal to infinity, that perturbation decays as you go to the interior of space. Similarly, in de Sitter, we were putting this positive frequency boundary condition, when eta goes to minus infinity, and under this analytic continuation, these two really go into each other. So, and recall that we even discussed that in order to really define things properly in the de Sitter context, we needed to rotate the contour slightly. And so if we needed to rotate it just slightly, we can just rotate it all the way, and we go to Euclidean anti-de Sitter. So these two calculations are really identical. So any calculation that you did for Euclidean anti-de Sitter can be immediately recycled into a calculation for de Sitter. All you need to do is change the radius to I times the radius. Okay, that's all that is needed. And this is true for also, I mean, this is so general that it's true in perturbation theory and so on. So and this is, of course, the familiar. So in flat space, we have the continuation from Lorentzian space to Euclidean space. Here in de Sitter, we have a similar continuation to Euclidean ante de Sitter. Well, a little more precisely, I should say, I mean, of course, you've also heard the statement that the correlation functions in de Sitter are analytic continuations of correlation functions in the sphere. Now, these are two different calculations, so depending on what you are computing, you would do different analytic continuations. So if you are computing expectation values in the Bunch-Davies vacuum, these are sometimes called also in-in correlators. So this type of correlators can be obtained by analytic continuation from the sphere. So we do this calculation, let's say, in the Euclidean sphere, and then to all orders in perturbation theory, we can obtain these correlators in the Sitter space. If instead we are calculating the wave function as a function of the metric, and the wave function as a function of the metric can be viewed as an inner product between a state with fixed metric in the future and the Bunch-Davies vacuum. I mean, the Bunch-Davies vacuum does not have a fixed metric in the future. It's a superposition of states, superposition of states with many possible metrics. And by computing this wave function, we're just doing this overlap. This is the usual thing we do, for example, for a harmonic oscillator where we take x contracting to the vacuum, 0, gives us e to the minus x squared, the usual wave function for the harmonic oscillator. Well, this is exactly the same in exactly the same situation is what we are doing here. These points were explained nicely in this paper by Harlow and Stanford. So we can turn, as I said, Euclidean ADS computations into de Sitter computations. And the simplest one would be to consider, so we heard in previous talks, the supergravity calculation of the sphere partition function. That can be done using gravity, using the Euclidean solution. We can calculate the gravity action for this context. That is what Marcos Marinho was talking about. He was computing this from the field theory context, but if you compute it in the gravity context, it's a simple calculation that you do by computing the volume of ante de Sitter space, the regularized volume of ante de Sitter 4. Now you can do that, and if you do this analytic continuation I mentioned before to de Sitter, we get just the usual Hartle-Hawking factor for S3. So we take psi, we take the modulus squared, so we take twice the result that Marcos Marinho was talking about, and that gives us the usual de Sitter entropy or Hartle-Hawking factor for S3. Now, less trivially, we can also take in principle, we could take any geometry that we had in ante de Sitter and do this transformation. So as a simple example, we could take, for example, a boundary metric, which is S2 times S1 with some radius beta. And the solutions in this case are, of course, the usual ante de Sitter black holes that have this boundary. And if we do this transformation, we get some metrics which are complex, but these are the metrics that we can use in the Hartle-Hawking spirit to calculate the wave function of the universe for these shapes. Okay. I mean, the metrics are complex because the Schwarzschild ADS background has a piece that goes like, some pieces that go like r squared, but the piece that goes like 1 over r, and when we do the calculation, the continuation that sends r to I eta, we'll get a complex factor. But as I said, there is no, in general, the metrics that we use to compute these wave functions are complex, so it shouldn't be a surprise that we get a complex metric for this computation. Similar things were discussed for scalar fields in a series of papers by these authors. They were evaluating the Hartle-Hawking wave function also for complex trajectories. That was a scalar field with the metric. Here I'm just discussing the case with only metric. Now, as a side comment, let me mention that this wave function is what should be identified with the partition function of a possible conformal field theory on the boundary. So if there was anything like the SCFT, the partition function of the CFT should be equal to this wave function. Now let me make a couple of comments about this. So we saw that this wave function has this behavior, leading behavior at the classical level. So if we evaluate the classical action, we'll get this term. If we were to evaluate the one-loop correction to this action, then we get a term that has this behavior. So it's now real. The reason we get something real is, again, we are doing this analytic continuation from, if we do this analytic continuation from ADS, this term has an R squared coming from this H squared. Sorry, sorry. So in this case, we, I'm not explaining clearly why this is real. But well, anyway, so you get something real here. And the reason we get something real is that you are forbidding these fluctuations in the future. So in the far future, we are forbidding fluctuations. And that's why we start getting real contributions of this kind. And the reason we are forbidding fluctuations is because we are putting a fixed boundary condition for the metric. And the boundary conditions we usually put in ADS-CFT or in computing these wave functions are always such that we first fix the wavelengths we are looking at, and then we take the cutoff to 0. So in doing so, we are always going to have the metric varies over distances which are bigger than the size of the cutoff. So the metric variations are always over super horizon distances. And that's the reason that we are forbidding fluctuations at short distances. And this is what we would need in order to have a correspondence to a possible CFT, because when we have a conformal field theory, we consider variations of the metric which are at distances bigger than the size of the cutoff. We don't include variations of the metric which are of the same order as the size of the cutoff. Of course, in a physical calculation, what we would like to be doing is to be integrating over all these short distance scales. This is what is most interesting to calculate. But that most interesting calculation will involve some average over all the short distance fluctuations of the metric. And that means the metric is not defined at short distances than the distances we are looking at. And that means CFT is not defined on a specific metric. We are really averaging over all metrics. It's not really a theory of, it's not a field theory. It's some kind of theory of gravity in some sense. Now, the fact that if we view a possible CFT as given by this formula, then we also remove some of the objections that were made about DSCFT. So, for example, one of the objections is that the zeta space will always decay. And therefore, the structure of the metric in the future will not be that of the zeta space, but will contain many bubbles with many other vacua, et cetera, et cetera. But if we are imagining that we're computing this wave function, we can just look at the part of the wave function where the zeta has not yet decayed. That amplitude will decay as we go to the future due to factors like this, except that, well, there will be additional factors of, if it's really bubble nucleation, it's a factor like this, but multiplied by the nucleation rate. And we could even include the possibility of having a boundary by saying that we have a field theory with a domain wall and another field theory here in the interior, or maybe the same field theory, and so on, as we are also doing ADS-CFT. Now you can view both the analytic continuation, these analytic continuations we were discussing, and the statement as either a glass half full or a glass half empty. So all the evidence for any possible DSCFT comes from this type of analytic continuation argument. So maybe you can say, well, there is no evidence for the SCFT. It just simply comes from this analytic continuation. Or you can take this as a hint that maybe there is some possible DSCFT. OK, that's all I have to say about this. Now let me discuss the relationship between calculations in ADS4, in Euclidean ADS4 or DS4, and conformal gravity. So what we will see is that this problem, which is a problem, is just a classical problem of computing the tree-level classical solution and wave function. So the problem we discussed a moment ago will show that this problem in 4 dimensions can be viewed as a problem in conformal gravity. Now, conformal gravity is a theory of gravity that involves the conformal class of the metric. So it's a theory that is invariant under Weyl transformations of the metric. So theory depending only on angles and not on distances. So 2 metrics that differ by an overall rescaling give the same action. So this is a gauge transformation of the theory. The action depends only on the Weyl tensor. So we have this W squared. And the action is explicitly invariant under this transformation. Now, the equations of motion of this theory are 4th order in derivatives. And for that reason, it leads to ghosts. And around flat space, the solutions go like e to the I. So for a fixed momentum, they go like they oscillate, and there is a piece that grows linearly in T. And then there are the complex conjugates. And due to this piece that has this T factor here, the flat space Hamiltonian is not diagonalizable. Has a Jordan form. Now, this relationship that I was mentioning between pure Einstein gravity and conformal gravity is based on 2 facts. One is the fact that the solutions of pure Einstein gravity are also solutions of conformal gravity. That's fact number 1. I'll show you why it is true in a second. And the second fact is that the renormalized action on de Sitter or Euclidean anti-de Sitter is the same as the action of conformal gravity on a solution of Einstein's equations. So when evaluated on a solution of Einstein's equations, that renormalized action is the same. And these 2 things are very easy to prove. They follow from a very simple relationship. Is the fact that if you write the Euler density, which is an expression quadratic in the curvatures, it can be written in terms of the Weyl tensor and contractions of Ricci tensor. And so if we had this action for conformal gravity, then the equations of motion come from varying this action. But this is a topological invariant, so that's the same as varying this action. And if we vary this action, this is roughly like the square of Einstein's equations. So for Einstein spaces, the variation of this can only be proportional to Ricci and the metric. So it must be if Ricci is proportional to the metric, it must be proportional to the metric. But since this whole thing was traceless, the coefficient here has to vanish. So an Einstein space will be a solution of the conformal gravity actions. Now, we look at the same equation, and we imagine setting R mu nu equal to G mu nu. This term will give something proportional to the volume. Okay? So W minus Euler is proportional to the volume. And the volume is exactly the same as the Einstein action up to a coefficient evaluated on shell. So when we evaluate the renormalized action, we're calculating the volume and subtracting some boundary terms. So we're taking this integrand and subtracting some boundary terms. But it turns out that these terms we are subtracting are precisely the same as the ones that we need to add here to the Euler density to make it into a full topological invariant, the Euler number. Okay? And so the renormalized action is equal to the action of Weyl up to something that depends only on the topology of the full space. So if we can select the Einstein solutions from the more numerous solutions of conformal gravity, then we can forget about the Einstein action and compute everything in terms of the conformal gravity action. And if we do that, then we get explicitly an infrared finite calculation. I didn't mention, but this is an expression which is explicitly finite. So it has no divergences as eta goes to 0. So we can set the boundary conditions at eta equal to 0, and then we'll get a well-defined and finite expression. And there is a simple boundary conditions that selects those solutions of Einstein gravity, at least for small fluctuations around anti-de Sitter space. And so the conformal gravity equations are fourth order. So we have two boundary conditions in the past from the Bunch-Davies boundary conditions. So we need two boundary conditions in the future to select a unique solution. So imagine that we put boundary conditions where we fix the metric in the far future, and we also fix the normal derivative of the metric. We set it to 0. That will give a unique solution of conformal gravity. But it turns out that this is also a solution of Einstein's equations, because now the Einstein solutions are such that when we expand them around late times, there is a constant piece, and then there is a piece going like conformal time squared, conformal time cubed, etc. And there is no piece that goes like conformal time. And therefore, this solution, this unique solution of conformal gravity that we found, obeys also this property of the Einstein solutions. And since we expect the solutions to be unique, at least for small deviations around ADS space or DS space, then since the Einstein obeys the equations, that must be the unique solution. So this is the boundary condition that selects the solution. One way to express this relationship is to say that if we evaluate the wave function of conformal gravity, which depends on the metric and the first time derivative of the metric, in a theory with that is fourth order in derivatives, the metric and its first time derivative are both position variables, and then the momenta that are conjugate are the second and third derivatives. And so we can choose to evaluate this at 0, and then we get the same as the Einstein action. Now, in terms of formulas, well, we had the Einstein action we mentioned before. We get expressions of the form w squared minus c with some constant, which is the Planck mass in Hubble scale units, or the radius, or the radius of ADS or DS. Now here, the sign of this term is such that it is minus. We get a minus sign here for the case of de Sitter, and for anti-de Sitter we get a plus sign. And this agrees with all the properties we normally know about gravity in these cases. Okay. And this is the only coupling constant of the theory, both viewed as an Einstein theory, the only dimensionless coupling constant. Now recall that the ordinary de Sitter wave functions, solutions of linearized Einstein equations, have this simple form. And of course, the fact that there are solutions also of conformal gravity explains this simple form. I mean, simply that they are the two solutions, the oscillating solutions that we discussed before. And this particular linear combination is such that it obeys the boundary conditions. So when we do this computation, we can do it in two ways. One is using the Einstein action with Einstein propagators and so on, or we can use the conformal gravity propagator and vertices. Now, what happened to the ghost? So all we are doing is we are really setting the ghost to 0 in the future. And a simple example is to choose a quartic field. So this is the action of a quartic field in Kerr space. It's conformal invariant. When we put it in around ADS space, we get an action which can be written this way. And then it can be written again in terms of two fields, one massless and one massive or tachyonic, depending on whether we are in DS or ADS. And what we are doing with our boundary conditions is setting this field to 0 at the boundary, and we set some non-zero boundary conditions for this field. So it's very simple. And all we are doing is just setting the field to 0 at the boundary. Yeah, maybe yeah. Now, so everything I discussed here was just the classical solutions, and it might be interesting just from the classical point of view to evaluate diagrams or to do calculations, because those calculations in conformal gravity are just done in flat space. You don't have to be in curved space. So it's a more complicated action, but you are just simply in flat space. Now, some versions of n equal to 4 superconformal gravity are also appear to be finite. So they are finite quantum theories. And so one of them appears from the twistor string. And so one can first ask a very simple classical question whether this truncation we did just for the case of pure gravity can also be extended to the full n equal to 4 theory. And it is likely that it will give an an O4 gauge supergravity, but it hasn't been shown explicitly. So one question we can ask is whether this could also work in the full quantum theory, whether the full quantum theory with this Neumann boundary condition can be interpreted as the result of a unitary bulk theory. I mean, normally we would say that a theory with ghosts will not be unitary, but here we are evaluating the wave function just at one time, only at equal to 0. And the equivalence between the ordinary gravity theory and this theory is only at equal to 0. So we could wonder whether if we did loop corrections, whether we would see unitarity violation or not. So we should be able to recognize if we expect problems with unitarity, and it would be interesting to understand whether these do appear or do not appear, or how they manifest themselves. I mean, what we're really doing is conformal gravity is essentially gravity plus a Pauli Villar's ghost field. And ordinarily we view the Pauli Villar's ghost field as being very massive, then we get pure gravity. But here we're making this Pauli Villar ghost field of the same order as the mass of the ordinary graviton. I mean, it's of the order of the radius of ds or ADS. And so the question is whether with these simple boundary conditions we can get a theory that is still consistent or not. I think the odds are small, but it would be quite interesting if it was true. So the conclusions is that conformal gravity with these Neumann boundary conditions is equivalent to ordinary gravity. Well, you can read the boundary. This is a nonlinear but classical or semi-classical relationship, and it would be interesting to see what happens in the quantum case. Now, we can ask about the situation in flat space, and exactly how conformal gravity is related to ordinary gravity in flat space. And one way we can get that is by taking a limit from ds or ADS gravity. In fact, this comment is independent of the relationship to conformal gravity. We can ask how are correlation functions of the stress tensor, or this de Sitter gravity wave observables, related to amplitudes in flat space. And this is a question people asked a lot in the past, how to recover the flat space amplitudes from ds or ADS amplitudes. And there is a very simple prescription in this case for 3 amplitudes, and it's the following. So if you have a bunch of stress tensor correlators, then you look, those stress tensor correlators will have a pole in this quantity. So this naively never appears to be 0, but you can analytically continue this case. So this is a function which can be analytically continued in the modulus of k, and we can make it negative. We can make one of these case negative in such a way that this develops a pole. And so if we look at the pole of nth minus 1 order, the coefficient of this pole is the flat space amplitude. Notice that this can be interpreted as the energy of the particles. For example, in the ds context, this could be interpreted as the energy of the particles. And because we are doing a calculation at equal to 0, or because of the expansion of the universe, energy is not conserved. But in flat space amplitudes, energy is conserved. And here it's recovered because we are looking at the coefficient of the pole, then the rest is evaluated on a configuration of momenta which conserves energy. So this is the relationship between this amplitude. This is something we're trying to check more in detail. But it's simply based on the physical argument that if you go to very early times, I mean, this pole comes from the very early times integral, and if you go to very early times, the fields feel as if they were in flat space, and that's why we get the flat space amplitude. There's a simple relationship between the two. I wanted to discuss some other application of conformal gravity, and that's in 5 dimensions. And so now imagine the same problem, but in 5 dimensions. And so we do exactly the same thing as we were doing before, computing the wave function of the universe in 5 dimensions. Now there is, similar to the 4D case, and we use again this ADS to DS analytic continuation, but there is one crucial difference. So, and that difference is that this factor that is multiplying the Euclidean ADS calculation goes like r cubed, and so when we do the analytic continuation, we get a factor of I, and because of this factor of I, we notice that these are even powers now, so we don't get any factors of I from here. And so all the terms, so initially we have something that is completely real. We do this analytic continuation, and all these terms continue to something, essentially all of them continue to something real. And so we get a pure phase, except for only one term, which is this log. So the log of epsilon continues to the log of the modulus of conformal time times I pi over 2. So we get here this simply this factor of pi, and times this term that comes from the that is related to the conformal anomaly of the theory. So we get this surprising result for the wave function of the universe in the 5-dimensional case. So this is a case where you can actually compute the wave function explicitly by this simple analytic continuation and simple properties that you all know. And in fact, you can check, for example, that for the S4, you get the usual Hartle-Hawking answer and so on. And one surprise is that it's completely local. It was non-local when we did it in even bulk dimensions. And something similar happens in any number of odd bulk dimensions. So for example, in DS3 gravity, we get only the Euler number, and so it only depends on the topology of space. Okay, so this in 5-dimensional de Sitter is this huge simplification when we compute the wave function. And this is again computing so the conformal gravity action now is the action that is the wave function that is giving the weights for the 4-dimensional slices of the 5-dimensional geometry at superhorizon distances. Well, something similar happens, I guess my time is up, but well, anyway, something similar happens in a relationship between rigid strings and ordinary strings, and I'll end here because my time is up. Thank you.
Questions?
So if you are calculating a Wilson loop expectation value, so after I wrote my paper, Sasha Polyakov pointed this out to me. So if you are calculating Wilson loop observables in ADS, then you can calculate them as Wilson loop observables in flat space, but with a different action. Instead of considering the Nambu action, you consider this so-called rigid string action. The rigid string action is an action for a string, for a surface, that depends on the extrinsic curvature, and it has the property that is Weyl invariant in target space. So this ordinary action is not, so you rescale the target space variable, the action grows like L squared. Here it's completely it's Weyl invariant. So if we have this action in, let's say, ADS, it will give us the same as the action in flat space. And so we compute with this action, but with an extra boundary condition. So we specify the boundary values of the field, and we also demand that the normal derivative is 0. So we specify both Dirichlet and Neumann boundary conditions, and then one can show that the on-shell value of the Wilson loop, the ordinary Wilson loop, minus the counter term, the usual divergent counter term, is equal to the finite value of the rigid string action on this type of solutions. So that's one relationship. And then there is the other relationship, which is similar to the one I discussed between 5 dimensions and the conformal anomaly and so on, which arises if you have a membrane in de Sitter or anti-de Sitter, a membrane in de Sitter. Imagine you create a bubble wall that is separating two vacua, let's say, either very similar cosmological constant or the same cosmological constant, so that we can treat the brane in a probe approximation. Then the action for this brane has a conformal anomaly that is proportional to the rigid string action. And for the same reason I discussed before about the factors of I and so on, here we get something that goes like R cubed, and we get a factor for the wave function, which is proportional to the rigid string action. So that's similar to, so that's the probability of having here a 2-dimensional surface with various shapes is given by the action of the rigid string action.
Any more questions?
Yeah, she does. Yes. Yeah, so the question is whether if you added matter, it would behave very differently from Einstein gravity. That's absolutely true. So if you want it to behave more or less like Einstein gravity plus matter, you have to add very special matter. So for example, if you added a gauge field to conformal gravity, right, then it would not behave like ordinary Einstein plus gravity. However, you can add, there is some, well, I believe, though I haven't completely checked it, I believe that if you, you can write an action which is also conformal for an object that has a 2-index stress tensor, whose action is essentially like the field equations of Maxwell. So d mu of f mu nu squared, that's the action for this field. And so that field then can be truncated into, I think conformal gravity plus that field should be truncated to Einstein gravity plus a Maxwell field. So I think that's how this n equal to 4 conformal supergravity truncation should work. But, well, this hasn't been worked out. But yeah, it would be very special matter, not any matter.
Okay, let's thank the speaker again.